Hi everybody. We're going to talk about questions 13 and 17 on exam 3. And let's look at problem 13 first of all. And this comes from the printout which starts on problem 12, I believe. And the first thing you have to do is figure out the T star, the test statistic. And you get that by taking the coefficient, which is 0.051381. and dividing it by the standard error, which is 0.00725. And when you do that, you'll get something to the effect of 7.087. Okay? Nothing too exciting there. And this is a T star, so we can't get the p-value directly, but it's actually given to us as 3.35 e to the minus 0.5. Now, don't panic. That's actually in scientific notation. So what we need to do is set it back into decimal form if you don't recognize that right away. And when you have scientific notation like this, you start out with 0 point, and then you have one less 0 than you have over here. So you've got 0.5 there, so you're going to have 4 zeros. 1, 2, 3, 4, and then 3, 3, 5. So you see that number is very small and very close to 0. Okay? Now when we use p-value, and we're going to use that as our rejection region, to help us set up our rejection region, so that would be as part of our step 3. So we would say if p is less than alpha, then we reject HO. We reject HO. Okay, so no matter what level we use for alpha, that p is going to be very, very small compared to that. Okay, and one of the questions that was raised is, what is a strong p-value, not so strong, and so on. Okay, remember we're comparing this against alpha. It's always a comparison. So, if it's close to alpha, it is not so strong. If it's close to 0, it is very strong. If it's above alpha, then we would fail to reject. That would be weak. Okay? So let's just say for argument, if it were 0.07, say, and alpha was 0.5, then we would fail to reject. Okay. Then on number 17, this is interesting. One of the questions was raised, do we always test beta 1 equals 0 versus beta 1 not equal to 0? And the answer is yes, and this is why. Let me show you. When you calculate your y-intercept term, you do something like this. Y bar minus beta 1 hat times x bar, right? So that's how you do it. Now, if beta 0, excuse me, my fault. Let me erase that. Okay, if beta 1, the population parameter, is equal to 0, then the estimate will also be equal to 0. So then when you go to plug this back in here, you're going to have y bar minus 0 times x bar, and beta 0 is equal to y bar. So that means your intercept term is simply going to be the mean of the y's. Okay? Why is that important, you may ask? Let me show you. It's the best way to show. Okay? So that's telling me that the best forecast or the best predictor that I'm going to have is that flat line at y bar. So no matter what value I put in for x, my predictor is going to be the same. Okay, so that means that regression is essentially not providing any information. Okay, no info. And you really need a different set of x and y variables to provide meaningful information. All right, so that's why you always want to test beta 1 equals 0, beta 1 not equal to 0. That way you know right away if you're providing any information. Okay, so let's go ahead and answer problem 17. Hang on. Okay, whoop. There. So our regression equation is minus 1. Let me just move the page here. Dog's jumping around. Minus 1.0279 plus 0.051381 x. Remember, that's an equation of a line. Okay, and what they want to do, they're giving us a value for x. That is x equal to 100. So we just plug that in where the x's are. Okay, 181 times 100. And then we have minus 1.0279 plus 5.1381. And when we do all the hand waving, you get 4.1102, which should be answer A in your questions. Okay? That's all there is to it. And watch the units on here. They're kind of sneaky about that. Every once in a while, they'll give it to you in some odd unit. So just kind of be on the lookout for that. All right? Good. Thanks.